Uh, I will be talking about building a climate model in Julia. I'm from the Naval Postgraduate School in Monterey, California, and I work in the CliMA Project, which was already mentioned yesterday in the first keynote, and it's a big collaboration between Caltech. It is led by Caltech and in collaboration with MIT, the Naval Postgraduate School, and the Jet Propulsion Laboratory. And we are building a new climate model that will automatically and continuously learn from observations. And machine learning and uncertainty quantification layer will then tell us where our parameterization of clouds and ocean turbulence or sea ice are uncertain, and then in those areas we will launch high-resolution LES type simulations that will automatically improve those parameterizations and give us information about things that we are not resolving. So that's the broad overview of the approach. And at NPS, we are responsible for the numerical part and the dynamical core of the model built using discontinuous Gherkin methods. We are developing the model completely from scratch in Julia. And already yesterday we also heard a lot about problems when using two languages, and especially if one is Fortran and you're trying to use GPUs and so on. This presentation will be mostly about our use of Julia and how we are using it and what's our impression so far. The code is completely open, available on GitHub. Feel free to take a look. Okay, so Julia. You probably, most of you heard the name and know a little bit about it, but I will briefly say a few things. So it's a dynamic high-level language originating from MIT pretty recently in terms of programming language age. It's 2009. And if you prefer looking at the code, then on the right I have some part of CliMA code, our linear GMRES solver, which is some basic textbook implementation, not the fancy stuff that we heard also yesterday, but just showing how the code looks. And Julia is really designed for scientific computing to solve the so-called two-language problem, where you prototype the code in one language, but to get performance you need to move to a different language. This is based on LLVM, and to prove that you can use Julia for building high-performance stuff and to not have to use another language, most of Julia is written in Julia. It can be used interactively and has features that we expect from a modern language, like a package manager. And performance, it achieves performance by just-in-time compilation and aggressive specialization. I will show an example in just a moment. And also has some very powerful metaprogramming and code generation, reflection capabilities. So to say more about how Julia really gets this performance while still being high level, On the left, I have some Julia function that multiplies its 2 arguments. I give to it 2 integers. You see that the function doesn't specify what type of language, what type of arguments it takes. It's a dynamic language, and since it's just-in-time compiled, I can ask for my compiled code, and on the right I see just basically integer multiplication. If I do the same with floating point numbers, I get floating point multiplication. If I take a floating point number and an integer, I get some operation for conversion and a multiplication. And this, of course, doesn't only work with primitive types, but I can use some library type. Here I use a static array, which is statically sized array. I use 4x4, multiply 4x4 matrix by a vector of length 4, and I still get quite nice assembly. At least I see code that ends with PD, which makes me happy. So this was a trivial example, but really this happens for any function that is can be very complicated, but Julia tries really hard to propagate all those types and generate code specific to the type. So in addition to performance, for our project, we think Julia is a good fit because it seems like a good common language for experts in machine learning and who typically know Python, and people in art science who may know Fortran, or if they know some high-level language, sometimes it's MATLAB, and so on. We are building a new climate model, so speed of development is very important to us, and ability to refactor the code quickly, especially since we want to try different ideas with this uncertainty quantification machine learning approach. And also we want to develop some of those capabilities independently and then combine them together. And Julia makes it really easy to combine together different modules, different parts of the model. This is a bit technical, but it's because it's not really an object-oriented language. It uses something called multiple dispatch to dispatch based on every argument type. And we also get some support from the Julia Lab at MIT. Basically, some of their PhD students do some work for us. Also, since we are building a new climate model, of course, we need to target accelerators and think about how we want to write code for accelerators. And Julia here, even though it's very recent, it's surprisingly does this surprisingly well. So I will present a little bit of the Julia GPU ecosystem. Most of this work was done by Tim Bessart, who now works at Julia Computing. And there are basically two main libraries and two different approaches. First is low level, called CUDA native, which in a few words, it's you can write CUDA in Julia, but it really deserves more words because it's a Julia CUDA compiler that is implemented as an external library, and it's designed so that it reuses the Julia compiler infrastructure. And to do that, they added some hooks into the code generation part of Julia, and then the whole compiler can be implemented in about 4,500 lines of code. Of course, knowing the fact that we have backend that is provided by LLVM. So this is one GPU compiler, but this library already inspired efforts for AMD GPUs and Google Tensor Processing Units. And there is another library called QArrays, which provides arrays that with storage backed by GPU memory. So that's useful even when using CUDA native. It also has, it provides this high-level programming model where you can program your GPU using only element-wise operations and map-reduce functions. And this works on both CPUs and GPUs, just the type of your array changes, but this programming model is of course very limiting. So in our work on CliMA, we use CUDA native extensively. However, we use it behind the scenes. There is another layer of abstraction that I will present in a moment, but first let me tell a little bit more about CUDA native. On the right there is an example code and showing matrix transposition in shared memory, very basic CUDA application, and for people who know CUDAs, it should be very straightforward to see that you really just write CUDA in Julia. And it's really Julia code. Everything here has a Julia type. Even careful observers may see that indexing is of blocks and threads is one-based, because Julia uses one-based indexing. Okay, so CUDA native works by leveraging Julia ability to generate the static code. And the main difference between this and CUDA is that it allows arbitrarily Julia code if it doesn't use any runtime capabilities, any runtime code generation, and so on. So this has its benefits because you can use some standard, you can use the standard library and also some third-party libraries direct in your kernels, and it sometimes works, but the drawback is that it's very hard to tell if it's gonna work, and even if it works, the performance may be very bad. But it also sometimes is good. But performance for simple code that reassembles something that we would write in CUDA is similar to CUDA compiled with Clang, because Clang also is based on LLVM. And debugging this code is a bit tricky. So as I said at the beginning of this slide, we don't use CUDA native directly. We have an abstraction layer, and I want to present it by showing the same example of transposition written in this abstraction layer here on the left. It's called GPUI loops, and the code is aligned, so you can easily see which parts are different and which parts are the same. And there are only a few important differences. Here, when we declare shared memory, we use a different macro because we don't have shared memory on the CPU. And similarly for thread synchronization, there's a different macro, but the main difference is here. Those loops that are written here, they have this weird structure where the loop takes a pair of indices and is also annotated by this @loop macro. So this, you can imagine, just does this loop on the CPU and takes the second index on the GPU and actually uses the first index to guard against out-of-bounds access. So basically the difference is those loop annotations, and the only special part is that in the GPU loops version, I have to synchronize my writing to my shared tile by closing those loops here, those inner loops over ty and tx, and opening them here because this statement just compiles to nothing on the CPU. Okay, so this abstraction was developed by a PhD student at MIT, Valentin Churavi, and it was designed specifically for our needs. It is inspired by Oka, which some of you may know, and people at NPS used extensively in the past. It also handles of math intrinsics, automatically translate exp to CUDA native.exp that you would have to write when doing CUDA native. It provides some additional optimization passes, inlining, FMA generation, and loop unrolling. And it helps also with debugging, since you can run your code on the CPU first. Okay, and one interesting note that this whole library that does all this stuff is less than 500 lines of code. So compared to other frameworks that do maybe more featured, but it's still very remarkable how Julia metaprogramming and code generation can. 5 minutes? Okay. So I will skip this. For distributed computing, I would just say we use MPI and some distributed array abstraction based on it. And I will show some performance numbers. So for performance on CPU, I compared CliMA to NUMA, which is an older code that was also developed at NPS, and it uses the same discretization. Basically, it's written in Fortran. I have some timings for a single core run with in 3D with 10 elements in each direction, polynomial order 4. And we see basically that CliMA is like 30% faster than NUMA. And I divided this time into the 3 main kernels that happen here: the volume, the phase, and the low storage Runge-Kutta update. So that's our time stepping. So obviously there are probably some issues on the NUMA side because this time stepping update is very large, but even when we look at the volume kernel, we see that we are a little bit faster, which is not that surprising because what we can do in Julia, we specialize our our kernels to the polynomial order, so it's known at compile time, which and it isn't in NUMA. Okay. So some strong scaling for the same problem. So I was happy with this scaling until yesterday when. So this is scaling on some cloud server because I couldn't get access for some time to our cluster, and this looked fine. We get similar scaling, maybe with some problems near the end. And then I ran this code on our cluster, which has more CPUs, still single nodes, so these are very preliminary benchmarks and so on, but I got this result, so clearly there is some problem, and our scaling is not very smooth compared to NUMA. So that's something that I will look into. And the final performance result shows a roofline plot on the Tesla V100 GPU, where I have my performance for in gigaflops per second and my arithmetic intensity. There are a number of kernels, and each kernel is identified by its shape, and the color corresponds to different floating point options. So red is 32-bit and blue is 64. And we basically see that we are everywhere we are bandwidth bound. There is this peak flops for double precision here, and a lot of our kernels sit very happy on the roofline, but they are performing quite poorly because they have low arithmetic intensity. The kernel that has the most performance is the volume kernel, but there is some small inefficiency here, and those are library reductions called from QArrays. So these are known to be poorly performing. Okay, so my conclusion, I guess I ran out of time, so you can read those. I will just say a few words about the outlook. So this was really the one significant benchmarking that we did since the project started. There was some initial benchmarking when we were deciding on the language, and right now we want to, and there's one person already working on it. We want to set up a performance continuous integration. We have continuous integration to check our model correctness, but we want to observe our performance. We would like to have more backends for this GPU loops and benchmark using multiple GPUs and multiple nodes. Okay, thanks.
Thank the speaker.